If you just finished the chapter focusing on containers, you're probably thinking to yourself, hey, these containers are really great. We should be using containers for everything from now on. Well, first, I love your enthusiasm. Let's keep that going. But now that we have a better understanding of how containers can help us, this lesson focuses on some of the challenges that container-based workloads present and how Kubernetes can help us. In our container chapter, we focus primarily on a single host running some containers. That might work in a lot of situations, but for most enterprises, they need to be able to run containers across a fleet of servers, or at least more than one server. Here we have 3 separate container hosts. Each one is capable of running container-based workloads, and the last server happens to have a graphics processor in it, so that it can be used for AI or ML workload processing, or crypto farming if that's your thing. You begin to deploy your applications to the container hosts. First, you deploy your container to one of the hosts. And of course, since this is a mission-critical application, we need to make sure that it's highly available, so we naturally deploy that container to an additional host in the cluster for redundancy. Your first application is looking pretty good. Nice work. But over time, you'll probably notice that many of the additional containers that have been deployed are being deployed on the first host, and it's starting to have some performance problems. Meanwhile, the other 2 hosts have plenty of capacity left over. Now, if you're a vSphere admin watching this, your first thought might be, wow, this set of hosts really needs some distributed resource scheduling, or DRS, which is a feature of vCenter uses to load balance virtual machines across ESXi hosts. If you thought that, then you're on the right track already. So let me introduce you to Kubernetes. Kubernetes provides a way to cluster individual container hosts together and provide some orchestration across them. Once our container hosts are added as part of a Kubernetes cluster, the Kubernetes scheduler can distribute our applications across the hosts so that they are more evenly distributed. This helps us not only with server utilization, but also availability by trying to distribute copies of our applications onto different nodes within our cluster to protect against a host failure. We can also use the Kubernetes scheduler to make intelligent placement decisions for us. For example, we may have an application that can really benefit from having access to a graphics processor. Since our cluster only has one node with a graphics processor in it, the Kubernetes scheduler can match applications with host features such as a GPU, so that our app gets placed on a node with a graphics processor on it without manual intervention being needed. Let's take a look at another scenario that container workloads might run into if they don't have something like Kubernetes to manage them. Here we have a pair of containers as part of our application. The source container is presumably a web server or application server that needs to connect to some back-end service such as a database or an event bus or something like that. The source application has been configured with either the DNS name or IP address of the back-end container that it needs to communicate with over the network. If that container crashes or is stopped for some reason, the container engine can be configured in such a way as to restart any failed containers. This does not mean that the replacement container will use the same network address as the container that failed. This means that our source container no longer knows where the backend container is at, and the application is now broken until someone can reconfigure the connection to the new destination container address. Kubernetes can help us with this issue as well, in a couple of ways. First, Kubernetes helps us with service discovery. Every application deployed into a Kubernetes cluster can be deployed with a Kubernetes service, which knows where the containers are running. The source container points their connection string to the DNS address of this Kubernetes service, which directs the traffic to the correct destination containers. When a container fails, the Kubernetes scheduler restarts a container, and the destination service is updated with the correct information about the new running container. In this scenario, the source container didn't need any modifications because the service automatically updated with the correct endpoints for the destination container. Also notice that since Kubernetes orchestrates resources across container hosts, that the replacement container was restarted on a different host in the cluster. This also provides a Kubernetes cluster much more resilience than a standalone container host. I also want to point out that as a good practice, these Kubernetes services should also be used with more than one container, so that if a container or host crashes, traffic can still be served by the other running containers behind the service, until that failed container can be brought back up. In this way, you can really think of Kubernetes services as a load balancer that runs within the cluster. Hopefully, you've got a better understanding of why we might need Kubernetes to help us with the orchestration of containers. I've showed a couple of simple scenarios to demonstrate why Kubernetes is needed on top of a container host, including service discovery, availability, and workload placement. There are plenty of other advantages to Kubernetes, like the ability to do rolling updates, horizontal scaling, and health checks, but I think this quick overview should have made the point that Kubernetes might be needed on top of our container hosts.